going to move on to the next section, quantifiers. All right. Okay, we had this question before. Recall, x is an integer. It's not a proposition. Because we cannot decide just yet whether this is true or false. However, if x is determined, it is a proposition. For example, if x equals 2, 2 is an integer, is a proposition. A square root of 2 is an integer, is a proposition, like that. So this kind of thing is very useful in mathematics. So we define this. So let's say P of x is a statement involving a variable x. It's like this. X is an integer. It's a statement involving x. And D is a set. We say that P is a propositional function with respect to D if the following condition is true. For every element x in D, P of x is a proposition. Right? So it's like this. But we have to decide this D. And D is called the domain of discourse. Domain of discourse. So the definition of propositional function. Propositional function. So it's a function. What is a function? So function means you receive something and then it gives you some value or anything. That's what functions do. So you receive x, then it will give you a proposition, like this. If you give x, like x equals 3, it will be a proposition. 3 is an integer, just like that. So one can think of this P as a function, because it says, explicitly says that function as a function like this. Function which is a function from domain to TF. It gives you true or false. It's a proposition, so it has truth value, T or false. So you may think of this as a function like this. This is why it's called a propositional function. Okay, some example. I'm going to use the same example like this. So it is very important to decide this domain of discourse. Whenever we say a propositional function, it should be mentioned what the domain of discourse is. So here, definition of example. Let's say P of n is this statement. N is an integer, like before. D, then P of n is a propositional function with respect to, this means with respect to domain of discourse you can choose domain of discourse as you wish. Domain of, let's say, domain of discourse is R. So P of 3, this means 3 is an integer. It's a statement which is a proposition which is true. So it's a true proposition. P of square root of 2 is a statement saying square root of 2 is an integer, which is, of course, a proposition which is false. Like that. And when we have a propositional function with given domain of discourse, it is very common to say something like this. P propositional function with let's just say with domain of discourse. Domain of discourse just so whenever I say D, capital D, it will represent the domain of discourse. This notation, P of X, this means this is a proposition, by the way. For every X in the domain of discourse D, P of X. So you can read this as for every X, P of X, or for all X, P of X. Example. For all X, statement is like this, where domain of discourse is R. So what this means is that for every X in D, which is the set of real numbers, X squared is greater than or equal to 0. Is this a statement? Proposition? Yes, it is a proposition. Do you think it's true? For all real numbers, its square is greater than or equal to 0. Yes, it's a proposition and it's true. Okay. So when is this false? So for all X, P of X is false if for at least one X D, P of X is false. If you can find just one X, at least one X in your domain of discourse, such that P of X is false, this is false. Otherwise, it's true. True otherwise. Okay. Yes. Oh yeah, this is when I use this. A value X for which P of X is false is called a counterexample. To this statement, proposition, for all X, P of X. It is a counter. If there is such an example, it's called a counterexample. So this is true if P of X is true for every X. Otherwise, you will have at least one X such that P of X is false, and that is called a counterexample. In that case, this proposition is false. So let's look at this. Domain of discourse is again the set of real numbers. This is a statement. Is this statement true? So this proposition says for every x in real number, in the set of real number, x squared minus 1 is greater than 0. Is this true? No. You can find a counterexample. What is a counterexample? This is false. Counterexample. There are many, but you can find, you need only one. Counterexample. X equals 0. If x equals 0, then x squared minus 1, which is minus 1, is not equal to 0. Or not greater than 0. So, counterexample. So, it's false. Oh yeah, there are many different ways, similar but a little different ways to say this. They all mean the same thing. We also say for all x, p of x, this means for arbitrary x, p of x. In mathematics, people often say this or this. They all mean the same thing. For any x, p of x, or for every x, they all mean the same thing. And they are all denoted using notation like this. If I say for all, or arbitrary, any, every, you should understand this as this. All right? All right. So we've learned this notation for all. There is a parallel notation to that. This E. This is similar to E. This means there exists x such that p of x. So this is the notation for this. There exists x, p of x, such that p of x. This is true. When is this true? If there is at least one x in the domain for which p of x is true. If you can find just one is enough. Just one x, element x in your domain of discourse, such that p of x is true, then this sentence is true. This proposition is true. So let's see an example. There exists x squared plus 1 equals 2 over 5. Domain of discourse is R. We have to specify the domain of discourse always. Is this proposition true? Can you find x in real number such that this proposition is true? Yeah, it's true. X equals, let's say, 2. If, then x, this is true, right? So we found just one, and that is enough to conclude that this is true. So it's true. You don't have to consider other things. There can be more examples or not, doesn't matter. If you found one thing, that is enough. You don't have to consider, you don't have to find all solutions of this to determine whether this proposition is true or not. Another example. It is also common to write this way. There exists x in R. So this means the domain of this course is R. So because it takes time to write, to say all the time, like the domain of this course is this. So instead of doing that, we can say, we can write this way. Is this true? if this is true, you should be able to find one real number such that this inequality holds. Can you find such an example? Actually, this is false, because for every x, this is not true. For every real number, we know that x squared is greater than or equal to 0. The square of every real number is at least 0. So 1 plus x squared is greater than or equal to 1. So because both are positive, you flip the numerator, denominator, you get this. So for every x, you cannot have this. So there does not exist an example of this. So it's false. So for existence statement involving existence, if you want to show that this is true, all you need to do is find just one example. But if you want to show that this is not true, you have to prove something like this. You have to consider all possible values of x. All right. Okay. Is it okay? All right. Yeah, there is a theorem, 2 parts. There is some relation between for all statement and the exist statement, existence and this. If you negate this proposition, you get you change for all to there exists, and there exists to for all, and like this. They are equivalent. These two are equivalent. So what this means is that it is not true that for all x p of x. And the correct way to rephrase this is to say there exists x such that p of x is not true. Something like that. Let me prove this. Just for one, I'm going to prove this. This is kind of standard argument. So we want to show that two propositions are equivalent. What does equivalent? What does that mean? Equivalence of two statements, two propositions. They have the same truth value, no matter what x is. For every x, they have to have the same truth value. They must have the same thing. So suppose that is true. So in order to show that these are equivalent, you can just show it like this. If this is true, then this is also true. And also, if this is false, this is false. So we need to show two things. If this is true, this is also true. This is false, also false. So I'm going to consider two cases. The first case is when this is true. So this is true. What does that mean? That means the inside thing is false. Is false, right? That's what this means. This is false. This proposition false means there exists x for which this is. So not everything satisfies this. Yeah, this is just, this means there is x in the domain of this course, which I didn't specify here, but such that p of x is false. Because that's what this sentence means. Otherwise, it would be true. All right? And we can rewrite this like this. There exists x such that not P is true, right? So, right? So this is true in this case. So true implies this is also true. Yeah, this is kind of obvious, but yeah, I'm gonna show. I just want to show you how we prove equivalence of two things. Now we have to consider the other case as well. Suppose that this is false. What does that mean? For all x, p of x is true because we negated this false true. This means what? For every x, I just rewrite this. P of x is true. That means there is no x such that P of x is false. Right? I just rewrote this. But that means there exists x, P of x is false. Right? Because this means this is false. So this is basically the proof of this. If this is true, we just showed that if this is true, this must be true. And also, if this is false, then this must be false. That means they always have the same truth value. If this is true, this is also true. If this is false, this is false. The second one can be proved in this same way. Any question? Yeah, but this is merely just rephrasing equivalent statement. All right. See some example. There exists Rx in R, x squared minus 2x plus 1 equals 0. Let's consider this. Is this true or false? There exists x in R, for which this statement is true. True? Yeah, because you can find such an example. X equals, say, 1. Yeah, it's true. You just found one thing. This is enough. This is a proof, basically. Proof of this. And there exists x in R. X squared plus x plus 1 equals 0. Now this is false. You can show that this is always greater than 0. For every real number, x squared, let's look at this. You can rewrite this in this way, x plus 1 over 2 squared plus 3 over 4. They are the same. But this is always non-negative, so it's always greater than or equal to 3 over 4, which is obviously greater than 0, so it cannot be equal to 0. So it's a proof that is false. All right. Okay, let's use the previous theorem, maybe in the next slide. This very famous sentence, not everything that glitters is gold. This is famous sentence that we have heard of. So let's try to express this using the formal language that we have learned. P of x let's say X glitters, and Q of X, X is gold. Okay, so the domain of this course here, what can it be? Everything? Yeah, just literally everything. Domain of this course is the set of everything, let's say. All right, so this, now we can write in this way. Not, this is the correct way to write this. Everything, for everything, P of X, if P of X, then Q of X. This is not true, right? This is one way to write this using notations that we learned, right? Do you think these are the same? For everything, the fact that it glitters doesn't imply that it is gold. So these are basically the same thing. So there is another way to write this using the theorem that we just learned. So we can move this inside, right? So the existence is changed, for all is changed to there exist. Not this, right? But in fact, this is equivalent to this. Not this means P of X, but not Q of X. These two are equivalent. You can show that. No, not P. Oh. This is equivalent to not P and not Q. All right. So what does this mean? This means, in words, there is something that glitters, right? That glitters, and that is not gold. So this statement here is equivalent to this statement. Do you agree? Not everything that glitters is gold. That means there is something that glitters but not gold. They logically mean the same thing. But you can check this using the theorem that we learned. So if you learn this kind of logic or properties of logics, you can be a more logical person if you want to be.